electrons are accelerated and the magnetic confinement of the electrons in the ring needs to be ramped up at the same time. Yeah, because more energetic particles need a stronger electric field to be kept on the same trajectory. So most, I think all modern synchrotrons have these two stages. One real synchrotron, which serves as a pulsed accelerator. Yeah, of course, this ramping up of the acceleration and of the magnetic confinement can only be done for a short period of time. And then the electron bunch that is accelerated is injected into the main storage ring, and the actual like the light source with these undulators in the storage ring, this should be called a storage ring, not a synchrotron in the strict sense of the word, because here then the energy is kept constant, and in order to keep the energy constant, still the electrons have to be constantly accelerated. So there's this radio frequency cavity that you can see here as this copper box. But that is just to compensate for the energy loss that the electrons experience as they continuously emit synchrotron radiation, right? Because remember, in every bending magnet, the electron beam emits radiation. In every insertion device, like in every undulator, the electrons emit radiation. So this, of course, makes them slow down and lose energy. And that energy needs to be like refed into the system by constant acceleration. Okay, before that, then okay, this is a view in the real life. That is the Swiss light source in Switzerland. Just where you can see on the left-hand side, this like bent structure. This is one small section of the actual storage ring where the undulators are installed. So maybe this blue thing could be an undulator, I'm not sure. And on the right-hand side, this inner bent structure, that is the booster ring, which since the Swiss light source is a much larger facility here, the booster ring is incorporated in the inside of the actual main storage ring. In the similar way as shown here. So you have a booster ring inside that like accelerates the electrons to the final energy before injecting the electrons into the main storage ring, which is then where the electrons are kept at constant energy. And even before the booster ring, the electrons have to be pre-accelerated. So what we can do now is go step by step, like follow the path of the electrons from their birth in the electron gun through a first acceleration stage, then a second acceleration stage in the booster ring, and then eventually we'll get into the storage ring, and then from the storage ring, we will follow the path of the light emitted from the undulators into the beam lines. So the starting point is the electron gun, the electron source. And in, I think, even modern synchrotrons, this is the very simple method of thermionic emission. So we start with a hot filament, which is like similar to in the old days, light bulbs had a tungsten filament that is just heated to very high temperature by sending a current through, and the emitted electrons are then accelerated through a circular, like a ring-shaped anode. This produces typically electron currents on the range up to 1 amp. And then the electron beam gets fed into the next acceleration stage. And the next acceleration stage, this could be a linear accelerator, something like this. And the way a linear accelerator works is, or at least this type, it's a radio frequency accelerator. The way it works is basically by having one cavity where a radio wave is kept inside the cavity and oscillates back and forth in the cavity, or if it's a whole like a real linear accelerator, like as a stack of these radio frequency cavities, like shown in the back here, then this is just a series of these cavities. But the way it works is that in the cavity we have this, we feed in through an antenna an intense radio frequency electric field, which oscillates in this cavity back and forth. And now when an electron enters from the left into the cavity and it just experiences the right phase of the electric field oscillation, it will get accelerated out to the right. Of course, in the next cycle of the electromagnetic wave, the polarity will be reversed and the electric field will point in the opposite way, which would cause a slowing down of the electrons. So obviously this doesn't work, so we just don't send in any electrons and we wait until the radio frequency wave switches sign again, and then the next bunch of electrons enters the radio frequency cavity, gets accelerated, flies out again. Yeah, so that you can see the radio frequency voltage that is sinusoidal on the right-hand side here. And this voltage, I mean, the electric field times the charge of the electron gives us a force. So when the electric field is pointing upwards, then or to the right, then the electrons, or actually to the left, because the electrons carry negative charge. So electric field to the left means the force points to the right. So all along this upper slope of the radio frequency wave, the electrons will experience a force to the right and they get accelerated to the right. Then in the next half cycle, the force would point in the opposite direction. So we just don't inject any electrons. So this principle already tells us or shows that electrons come in bunches, because only those electron bunches that have the right phase with respect to the radio frequency wave, only those bunches of electrons actually get accelerated, whereas electrons being outside of the bunches would experience the wrong phase and they would get slowed down. So that's the principle of a radio frequency accelerator. And those okay, these are two historical accelerators, but if we concentrate on the right one, the microtron, this is essentially a combination of this type of a radio frequency accelerator in the upper part here, where every time the electron passes through, they get a kick, like they surf on this wave and get accelerated. And then as the electron passes through, okay, here it starts in the blue point, it passes through once, gets accelerated, the radius of curvature of its orbit increases because it's more energetic now, but still it makes it around, goes through, gets accelerated a second time, the orbit again is larger, and so on. So this happens 1, 2, 3, 4, 5 times, and after the fifth acceleration stage, the electron then travels on an orbit which makes it be ejected out of this microtron, out of this magnetic field, which confines the electrons on the cyclotron orbits. And then the electron, those electrons have the same energy. They have all undergone 5 times the radio frequency acceleration, and then they would travel on with a kinetic energy of this should be electron energy on the order of up to 30 to 50 mega electron volts. And like the next the next generation of this type of microtron, it's called racetrack microtron. This is actually the accelerator type that is used at the Astrid synchrotron that we were just looking before. It's the same principle, only that this magnetic field section is split in half and like pulled apart, such that in the middle we have now a longer path where we can install several of these radio frequency cavities, and then increase the acceleration by just having the electrons travel through 5 radio frequency waves, and then racing around the racetrack again 5 times before being ejected and then going into the booster ring. So this racetrack microtron is installed somewhere inside the Astrid 1, this first booster ring. Then electrons are injected into Astrid 1, get accelerated in Astrid, which is really the synchrotron in the sense that it's being ramped up periodically, and then electron bunches are injected into Astrid 2. And this happens actually, so you may wonder how often does this injection happen? And I mean, do we, like every electron bunch that would be injected into the main storage ring, would it be kept there for a long time? And I mean, it would likely decay over time. And yes, it does. So modern synchrotrons nowadays operate in a way that these electron bunches are repeatedly injected into the storage ring. Then the bunches are left alone to cycle around many times. And as their intensity has dropped, because like electrons, as they fly around, will constantly collide with residual gas atoms, and some of them will also collide with the walls uh, of the pipe and so on. So we will, of course, continuously lose electrons. So after a certain while, we would then re-inject the next bunch of electrons. And this mode of operation is called the top-up mode, because the storage ring is continuously topped up with fresh electrons. And you can actually see, actually we could have a look on the website of Astrid, because I think Astrid has user operation right now. So in most of these synchrotron facilities, you can actually follow in real time. Always this top bar covers the top bar covers the, yes, there we go. So this is the website of the Astrid synchrotron, and we can look at the status. And for example, B Astrid 2. So this is a real, you can see in real time the electron current. That's the beam current. That's the number of electrons in the storage ring right now. And you can see that this like continuously progresses and continuously decays. Yeah, now it was now just updated. Continuously decays exponentially actually, and then how often is this? This is 20 minutes, so every 10 minutes or so, the storage ring is refilled with electrons, and the electron current is topped up to an average value of about 180 milliamps. Right, so this is the real time chart of the beam current in Astrid 2 storage ring. And then the blue and the green are some additional machine parameters. For example, the green shows us the lifetime, 20 seconds. The green shows us the lifetime of the electrons in the storage ring, 20 seconds, and so on. Anyway, that is Astrid 2 in real time. Then comes a little exercise. So we have learned that the electrons are produced in bunches, because only bunches of electrons get accelerated through the radio frequency accelerator in the right phase, because these electrons travel, like they surf on the wave, on the radio frequency wave at the right phase to get the maximum acceleration. And then the electron bunches are injected into the storage ring and orbit around the storage ring. The question is, like we have a storage ring, Astrid 2, of a circumference of 45.7 meters. There's a beam current. Okay, it's actually 180 milliamps. We have just seen it's not 200. Lifetime, okay, in the top-up mode, it's infinite, but we have just seen the actual electron lifetime is more like 20 seconds. We have a radio frequency in this radio frequency accelerator that continuously accelerates the electrons to keep them at the constant energy of 580 megavolts. And this radio frequency accelerator operates at 105 megahertz. So from these data, please try to calculate what is the repetition rate of the bunches and what is like at what spacing in time between the bunches do the bunches come and how many bunches are there at all in the ring. This is now a little exercise. Please take a minute and think about like how many bunches actually travel around this storage ring and what is the distance in time, but okay, what is the distance in space? You could also calculate that and then divide by the speed of light because the electrons are almost at the speed of light, so that is equivalent. So how would you go about it? How many bunches are there in this ring of circumference 45.7 meters? Any ideas? How many bunches? So remember, the bunching comes from the fact that electrons have to travel through the RF accelerator always at the right phase of the RF oscillation. And the RF oscillation happens with a frequency of 105 megahertz. So a bunch travels through like a bunch length is or the distance between bunches is essentially given by the period of this radio frequency oscillation, right? Because only for every next period of the radio frequency, the next bunch would come in with the right phase. So what's the period of, or what's the wavelength of the radio frequency? And how can we calculate from the wavelength of the radio frequency? How can we calculate the number of bunches in the ring? Any ideas? Is this too obvious or is this too difficult? Or is everybody fallen asleep already? Can anybody give me feedback? I mean, those of you who have worked at Astrid, Rajni, for example, I think should have an idea of how this works.
I am still thinking myself.
So, I mean, yeah, we have the radio frequency waves. For every radio frequency wavelength, we get one bunch of electrons that travels at the right phase through the accelerator and gets accelerated. So what's the radio frequency wavelength? That determines the distance between bunches, right? How do we calculate the radio frequency wavelength?
Can we calculate the revolution frequency?
Okay, you mean the revolution frequency in the whole storage ring?
Yes.
Okay, that's probably given by the circumference, right?
Yes. So speed of light
Correct.
divided by the circumference.
Yes.
Mm,
And
okay.
so that would give us the revolution frequency.
Yes.
But I mean, the question was, so that is the frequency for one bunch to orbit around but the question was, how many bunches are there? And what's the distance between the bunches? So there's more, I mean, I can tell you there's more than one bunch orbiting around.
Then from the frequency, we can calculate the time and divide by the 105. I don't know.
Okay. That's a good idea. So, okay, that would be the revolution frequency. And then, I mean, the revolution, okay, so I mean, we can do that. So speed of light is 3 times 10 to the 8 divided by 46 meters. So this will roughly be 10 to the, a little bit less than 10 to the 7, right?
Yes. 6, 10 to 6.
6, 10 to the 6, yes. And then, and then we have the radio frequency, which is 100 megahertz. So this is 10 to the 8 hertz. Okay, and then if we take the ratio, what do we get?
Yeah, it's 16.
Yeah, 15.
15, 16,
And
yeah.
yeah, I mean, that is one possible calculation. The way I thought to do it is like to first calculate what is the period of the radio frequency, because that determines the time period whenever the next bunch arrives into like from the accelerator. That would be 10 nanoseconds. This corresponds to a wavelength of the radio frequency of 3 meters, and then just take the circumference of the ring divided by the wavelength. 45.7 meters divided by 3 is 15 bunches. But I mean, the calculation that you did is the same, so it gives the same result. And what is the spacing in time between like the repetition period of the bunches then? How do we get that?
won't it be same as the repetition time? Because that's where each bunch is coming from the accelerator, right? So the
Yes,
accelerator.
exactly. You're exactly right. So that is just given by the repetition period of the accelerator. This is the frequency or the time period at which the electron bunches are spit out of the accelerator, and that is every 10 nanoseconds. Yes. So this is, I mean, just for the idea was to give you some orders of magnitude of like how many bunches at what typical spacing in time between the bunches, and also the pulse width, so the duration of the synchrotron light pulses. This we cannot calculate directly from these parameters, but this is always in the range between 10 picoseconds and 100 picoseconds. So this shows you that actually sometimes the synchrotron radiation is also called quasi-continuous, because the ratio between pulse on and pulse off is actually not very large. It's 100 picoseconds versus 10 nanoseconds. This is only a factor of 100. Yeah, only like the off time is 100 times longer than the on time, and the repetition period is very short, and so the repetition rate is very fast. So in most of the synchrotron experiments, actually, we don't even notice that the radiation comes in pulses, but we consider that the radiation is pretty much continuous. And that is also very different compared to free electron lasers, where the off period between the pulses is much longer, and the pulse durations is much shorter. So there we really have to consider that the pulses come in very short pulses only every once in a while, whereas at synchrotrons, the radiation is quasi-continuous. All right, then let's continue with going now along the beam lines. How are we doing with time? Okay. Oh, 1:30. Ha. Okay, I think it's almost Tanuf or Shiva. Should we continue for a little bit more, or should we continue on Friday?
Marcel, if we are starting a new topic, maybe we could even do it Friday,
Yes, all right.
unless you say some prelude is required today.
No. This is just now move. So far we have discussed all the main components along the accelerator and storage ring. Next topic will now be following the undulator radiation along the beam lines. So it
Okay.
is kind of a new topic, then I agree. Let's maybe stop here for today and then reconvene on Friday.
Sure, Marcel.
All right, then have a nice evening. And
Professor Marcel, just a small doubt. So
yes,
actually, we do have a list of students who actually put their interest to do the presentation for certain publications. That's a list there. So like, it's there in the schedule. The students
I
in the
know
list.
it's me that made the list.
Okay, they
It's
have put
this
their
one.
name. Yeah. So will it be possible to tell the tentative date so that we can be ready for it, or anybody else would be interested to join? I'm not sure. All put the name for that.
Yeah, absolutely. So like very tentatively, I have put a date here to this first topic, because diffraction imaging was supposed to be one of the first like applications of free electron lasers to be discussed. The next topics will come later, but I mean, now that we are getting closer to that date, let me put some tentative dates for all these topics that we have until now. And yeah, so I will do this right away. You will see that your dates will probably be end of next week, or then the week after. Okay, I'll put some dates in here.
Okay.
All right, then see you on Friday.
Thank you.
To
Thank you,
Marcel.
Thank you,
Shiva,
sir.
can we
Yes.
just stay in the loop because stay in the call because yeah, it's actually not exactly clear to me how we should proceed with the schedule. Because I mean we have Christmas times coming up, and
Yes.
how is it with you? Like you are just continuing to there's no end of the year break or anything like that whatsoever, right? Or is there?
Well, not that it's a custom, but I have 2 breaks, one for Christmas, few days before Christmas, and Christmas, just taking advantage of that.
Mhm.
And then I'm just making a little year and New Year trip for 3 days. So between 31st and 2nd January, I'll be off, but I'll be back on 3rd January again. So we could. So you're also off for Christmas, Marcel? And
Yeah, I mean, I'm like this kind of lecture I could easily do also over the holidays. The main thing is that on like 22nd and 23rd there I have to travel. I'm traveling to Aarhus because like I'm currently selling my house and I have to go there one more time to pick up the last remaining stuff that's still there. So that will be 22nd, 23rd. So that does not fit me very well. But thereafter, and okay, and 24th is Christmas Eve. So this also would be
let's
would
forget
be
until 26, Marcel.
okay. Yeah, thank you. Yes,